So this is the tutorial on practical numerical optimization using scipy, Estimagic, and Jaxopt. We chose those libraries because they complement each other well. And the term practical should emphasize that we are not presenting a lot of theory about numerical optimization or a lot of background on the algorithms, but that we really want you to get your hands dirty and solve some practical problems. I'm Janos. You can find my webpage and GitHub handle here. I started Estimagic in 2019, mainly because I was doing a lot of numerical optimization in my research and was a bit frustrated about how long it takes to switch between different libraries and find the right optimizer. I just submitted my PhD thesis last week and will be looking for jobs soon. Tim?
Yeah, so I'm Tim. You can also find my website there and my GitHub handle. I have been contributing to Estimagic for the last 2 to 3 years and now consider myself a core contributor. And I'm also a PhD student in economics, but I still need a couple of years until I finish.
Okay, so we have roughly the following section. First, a very brief introduction on what numerical optimization is and how to do numerical optimization in scipy.optimize. Then a quick intro to Estimagic, followed by short presentations on specific topics. A main focus is how to choose the right optimization algorithm for your problem. And finally, we talk a bit about Jux and Jaxopt. Before we really start, maybe a few questions. So, who of you has done any numerical optimization before? Okay, so most. Who has used scipy.optimize for that? Probably none has used Estimagic. And has anyone already used Jux or Jaxopt? Also, okay, one. Yeah. Okay, so the very first part might be will be very trivial for those who have done previous optimizations, but I think it's necessary to get everyone started who hasn't so far, and then the rest will be interesting for everyone. The structure of each topic will be the following. So first we give you a summary of the tasks that you are going to solve in the next exercise session. Then some theory or background knowledge that you need. Then we show the syntax or mechanics of how to do what you learned in the optimization library we are using. And then you yourself solve a more difficult example in a Jupyter notebook. And then Tim is going to discuss the solution of each exercise afterwards. Okay, so in the very first practice session, what you're going to get is the math description of a function to be optimized. And then you code that into Python and optimize this function using scipy.optimize. So this is a more simpler example than what you're going to solve. But it shows what are the ingredients for an optimization problem. So first of all, you have a criterion function. In this case, f of a and b. The criterion function is then just a squared plus b squared. So this is the absolutely the most simple problem you could imagine, and any numerical optimizer is going to be able to solve this. We have two free parameters, a and b. And what we are after is the optimal parameters, a star and b star, which are the argument of the function. In some cases, we are more interested in optimal parameters. In some cases, we are more interested in the actual function value at the optimum. This depends on the application. Possible extensions of such a problem could be that you have constraints or bounds, but we're abstracting from all of this for now. And the correct solution of this is actually both parameters are 0 and the function value is also 0. So how would we solve this using scipy.optimize? We import NumPy, import minimize from scipy.optimize, and then we define the criterion function that we just saw. So in scipy.optimize, the parameters need to be a one-dimensional NumPy array. The first step in the criterion function is that we parse this NumPy array into the two numbers we want to use, and then do the calculations. Could, of course, also take a dot product, but this is more illustrative. We then need to set up start parameters. This is necessary for almost all optimizers. And call minimize, passing the criterion function and the start parameters to it. And then the results object has a .fun attribute, which is the function value at the optimal parameters, and .x, which are the optimal parameters. What are the features of scipy.optimize? So minimize that you just saw is a unified interface to 14 local optimizers. They are for different use cases. So some of them support bounds, some support constraints. Some of them use gradient information, others don't. We are talking more about how to pick optimizers later. The parameters are in all cases 1D NumPy arrays. And if you want to do a maximization, you need to flip the sign of your function. So then you minimize the negative of the function. More importantly, you need to remember to flip it back if you need the optimal function value, because otherwise you're calculating with the wrong number. Scipy.optimize also has different interfaces for global optimization. I think there are 5 or 6 global optimizers, and for nonlinear least squares optimization. We'll talk about both of these topics later. Okay, now we start with the first practice session. So you've all cloned the repo. You can just go to the first notebook. Here you have the notation and math description of the function. And then 3 tasks. First, define the criterion function, set up the start parameters, and minimize the functions. And if you should have any questions about this, just raise your hand and we will come to your seat. And you have about 10 minutes or so to solve this, but we will ask until when everyone is ready.
I also have one more question. So if anyone knows or has a Windows operating system, we have a listener over there, and she has problems with her Windows installation. Unfortunately, we don't know Windows, so if anyone could help out over there, that would be very nice. So I'm going to present the solutions now. Janos already went through the problem description. We have the criterion function, f of a, b, c. We want to minimize that. And the first task is to just write out the criterion function. Now the problem is that with scipy minimize, we need a vector x, like a NumPy and array, 1D array. But the function is defined in a way such that we have a, b, c as parameters. So the first thing we have to do is we have to pass that. This is what we do here. If a is equal to x naught, b is equal to x from 1 to 4, and then c is all the rest, but it's a matrix, so we have to reshape that. But of course, there are also other ways how you can do that. It's all legit. Now the value is then simply given by this expression. It's very similar to the mathematical expression. And we return that. That's the solution for the first task. If you have any questions, just raise your hand. Okay, so the second task was to set all the starting parameters to 0. So the problem is 8-dimensional. So we just define, we use NumPy zeros with 8. So we have an 8-dimensional 0. That's it for the second task. Now the third task asks you to optimize or minimize with scipy. So we already have the criterion function f. We have the starting parameters x naught. So we can just use the scipy optimize minimized function using f and x naught. We get our result. Can look at the resulting optimal point x. And that's already it for the first exercise. Any questions? If not, then we will continue with the slides.
Okay, so now that you have used scipy.optimize for a simple example, let's look at some of the pros and cons of the library. Definitely a pro is it's very mature and reliable. It has been around, the interface is stable and nothing changes. And all the algorithms are completely debugged. You have no additional dependencies as you have scipy in most environments. You have a very low overhead. And there are enough algorithms for many use cases. However, compared to all algorithms that you find in open source pipe packages, the selection is rather limited. You have no parallelization. For example, the optimizer might automatically calculate a numerical derivative, and this could be parallelized but isn't. Or some optimizers could evaluate the function, the criterion function in parallel, but don't. Maximization is done via sign flipping, which is just a bit cumbersome and can lead to errors if you forget to flip the sign back. You get feedback only at the very end of the optimization. Now, this was in your example, it took maybe half a second or probably less, but some optimizations run for hours or days, and then it would be nice to have feedback earlier. And if it crashes, you actually don't get any feedback. And finally, as you saw in the example, having parameters as a flat array might be a bit limiting for some cases. Yes?
When you say there is feedback only at the end, can't you make it list one line of status per iteration? It's a very cutting sort of Indian.
Yeah, I mean, some people print their criterion value or the parameters or log. I think you can also specify verbosity level. But if you have many parameters, this is not very helpful as if you have it in the terminal output. But it's not like, this is definitely not a hard limitation that for which you should abandon scipy.optimize. Okay. So now I'll show you two examples from real projects. The first shows why maybe having a flat parameter vector is not a good idea. And I don't want to say that this could not be, like, you could write nicer code for this, and then it wouldn't be such a big problem. But this is something that you find if scientists use this library. So here, for example, you have I think 60 entry parameter vector, and it's parsed in all the different quantities that you might need in your actual calculations. Another one, this I learned very painfully, is if your code is not completely numerically robust, you run an optimization, think you will have a result the next day, and then after, maybe quickly or maybe after 5 hours, you get a linear error and everything is lost. Okay, so the idea of behind Estimagic was kind of to take the strength of scipy, but also provide a bit more convenience functionality around it and specifically address these limitations. So what you're going to do in the next practice session is you take the example that you came up with in the first. So you take the criterion function from the first practice session and optimize it with Estimagic instead of scipy minimize. This is very simple. You literally don't have to change the criterion function. And then in the second task, you're going to actually use Estimagic's strength and represent your parameters differently. And finally, you're going to do a plot of the optimization history, so of the function values and the parameter values that were tried. But first, let me introduce it. So what is Estimagic? It's a library for numerical optimization. Then we wouldn't have called it Estimagic. So the reason for that is we also have tools for nonlinear estimation. So if you want to do a maximum likelihood estimation or a method of simulated moments estimation, we can not only help with the optimization, but also with calculating the standard errors and doing inference. So the optimization part of Estimagic is basically a harmonized interface to scipy, NLOpt, Tau, and Pykmore and other packages. So we don't have many algorithms re-implemented in Estimagic. We just take existing ones, wrap them, and make them a bit nicer. And I mean, Python is often called a programming language with batteries included. So following that analogy, what we are doing is we take existing algorithms, plug in the batteries, and give them to you. You can use it almost exactly like scipy if you want. So this is, again, the example we've already looked at. You import Estimagic as em, and then call em.minimize instead of scipy.minimize. And the names of the arguments is a bit different, and the attributes of the result are also a bit different, but it's really easy to switch. One key difference is that there is no default algorithm. And this was discussed many times, but as you will see later, like there is no single algorithm that performs well on all kinds of optimization problems. And I think forcing people to think about the algorithm and choosing one themselves is probably like leads them to use more appropriate algorithms in the end. So a key difference is that parameters can be almost anything. We have an example here. This would be parameters as a dictionary, having an entry A, which is a scalar, B, which is also a scalar, and C, which is a pandas series. So in general, you can use NumPy arrays, pandas series or data frames or scalars, and stick them into arbitrarily nested combinations of lists, dictionaries, and tuples. And one special case is a data frame that has a column called value and lower bound and upper bound. This lets you specify the parameters and the bounds together. We're going to see more about this later. If there are any questions about this, simply raise your hand and interrupt me. If you run optimization, you get an optimized result. This is the string representation, so you get this if you print it or if you look at it in a terminal. The first line tells you a bit of a summary of the problem that has been solved and how many iterations were needed to solve it. You might think telling you how many parameters you had is not necessary, but if you have large problems and many constraints, you potentially don't really know how many free parameters you have, because some constraints might might fix parameters to a certain value. The second line tells you how much the criterion function improved during the optimization. The third line you only get if your optimizer, the algorithm that you chose, wants to tell you something, so it has some message that it wants to give you. And then in the second part, you have an experimental feature which we call a Convergence Report. So different optimization algorithms have very different convergence criteria. And just because an algorithm thinks it converged doesn't mean that it actually did in the sense of finding a true optimum or so. So these numbers here let you judge a bit more whether your algorithm actually converged. There are different kinds of convergence criteria, like has the function changed a lot, have the parameters changed a lot, relative and absolute terms. It's in general a good sign if you have many stars here, so if all of it tells you that it actually converged. Now, having said that, for very simple problems with gradient-based optimizers, you sometimes need only 2 or 3 iterations. In that case, this is not very informative. The optimized result also has attributes similar to the scipy optimized result. So if you want to continue doing calculations with your optimal parameters or optimal function value, you can access them here. If you want to know more about the success or not, a convergence message and so on, you can also do that. The optimization result also has a history. So this is a dictionary containing the function values and parameter values for each iteration. and also the runtime in seconds. This is mainly not for you to look at it directly, but is used by some plotting functionality. There's also a way to do persistent logging. You do that simply by doing the same call to minimize, but adding logging equals, and then this is a path to some Sqlite database. The database does not have to exist, simply need a path ending in DB. And then Estimagic will create this database and save the function evaluations and the parameters into it and some more information. Now, it is an Sqlite database because this really prevents data loss in almost all circumstances. For those who don't know, Sqlite was actually developed for application on a battleship where regularly things break down, but they didn't want to lose data. So even if you unplug your computer in the middle of an optimization, you don't lose any data and can resume it later. Important feature is that you can read this log during the optimization. Because of that, the log file can also provide data for an interactive dashboard that you can open in the command line. Finally, you don't need any SQL knowledge, which was actually important for me because I'm not very good at SQL. Because we have an optimized log reader. So if you ever want to access the history or anything directly, you can do that simply by using the log reader, instantiate it with a path to the database file, and then look at the full history or at specific iterations of the optimization. So usually if you have this case that you got a linear error some time after 5 hours maybe, you would look at the last parameter value that actually caused this and use this for debugging them. You can also do criterion plots. So this is also what would be shown in the dashboard, but you can do it in notebooks as well. To the criterion plot, you could pass an optimized result, a log file, or a dictionary thereof. And if it's a dictionary, then we use this for the legend entries. You can set monotone to true. This is very useful if you have extreme values somewhere in the history. So often at the very start, optimizers pick rather extreme parameter values, and then all the rest of the history looks just flat compared to that. So in that case, you use monotone equals true, and it takes the current best function value up to each iteration. You can also limit the number of evaluations you want to see in case the right tail is very boring, as it is in this case. You can also plot the parameter history. So each line corresponds to one parameter. Just as a reminder, in this example, the parameters were a dictionary with A, B, and C was a series. And all this label information is also used here in the legend, so it lets you identify each parameter. In general, the arguments to params plot are similar to a criterion plot, but there's one additional feature, and you can already see here with 5 parameters, this becomes hard to distinguish the different lines. So if you want to zoom in on a subset of your parameters, you can provide a selector. That's just a function that takes your parameters, the 4-parameter vector, and returns a subset. And then we only show the subset. And that way you can either do multiple plots or just focus on the thing that you are actually interested in. There's also maximize. Not much to say about it. We're not going to use it much in this tutorial, but if you do maximization, it's more convenient. And it just works exactly like minimize. Like there's absolutely no difference except that it does a maximization. For more advanced usage, you probably want to pass algorithm-specific options to customize your optimization. The primary examples are convergence criteria, stopping criteria, or some other tuning parameters. And you do that by creating a dictionary of algo options like this, and then passing it to minimize like this. So the algo options are harmonized in the sense that if two algorithms have the same options or support the same options, then they will have the same name. But of course, we cannot support all options in all algorithms because sometimes it doesn't make sense. For example, Bobica is a trust region algorithm, so it has a trust region radius. But if you chose some different algorithm that doesn't have that, we simply ignore it. A key design goal was that you can switch between algorithms with just changing the string, just changing the name. So instead of raising errors, we simply raise a warning if there are unsupported algo options because it might have been a typo, but otherwise we ignore them and continue. There's a large online documentation. It has the typical sections like getting started for a very quick introduction, how-to guides. So there's one notebook for every argument of minimize or maximize, and the notebook shows in examples and with explanations how to use it, and then API and everything else. So you can use this during the exercises, and we also provide links to more specific sections of the documentation at the top of the exercise notebooks. Okay, so now we would have a short break, and then you can continue, like get some water and so on, and then you can continue doing the next exercise, which is converting the previous example to Estimagic. You can also switch, do the exercise now and get water later, of course.
Okay, let's start with the solution to the second exercise sheet. So, the first task was to switch your criterion function, or first copy your criterion function and the start parameters from the first exercise sheet, and then switch it to the use of Estimagic. So, first copied that function and the starting values. And then using Estimagic, as we've seen in the slide, is very similar to using scipy.optimize, though the argument names are a little different. So we have criterion here, and that was f. And we have the params, those are the starting parameters, that was x0. Now we have to choose an algorithm, and in this case, we use scipy.optimize. Then we can access the optimal parameters using res.params and the optimal criterion value using res.criterion. So that was already the first task. Now the second task, a little bit more interesting, was to now use pytrees instead of these 1D arrays. So first of all, we had to adjust the function. So we have the new criterion function, new f. And now that x is not a numpy ND array, but it's a dictionary. So the starting parameters look like this. We have a dictionary with the entries A, B, C. First one is a scalar, second one is a 1D array of zeros, and the third one, C, is a matrix actually. And now we don't have to do all the parsing in the function f. We can just use the dictionary directly. Now, if we want to use Estimagic to optimize it, it's also pretty simple. We just pass the new criterion function, the new starting values, and it does all the rest for you. If we now look at the optimal parameters, they also have the same structure as the starting parameters. You can also look at the criterion. Now, for task 3, we were supposed to plot the results. So we're going to use the Criterion plot from Estimagic. And it looks like this. So Nelameet kind of does these steps and reaches the optimal value at some point. And now if we look at the params plot, we were also told to use a selector to select only the parameters A and B. You can do this via the lambda function. It looks like that. Okay, so any questions? Anyone had any problems? Okay, perfect. Then I'm going to continue with the next section.
Okay, maybe going back here. So you see that the Nelder-Mead algorithm has this pattern that it does basically has a step function where sometimes it makes a lot of progress and then not so much. And it took, for example, 4,000 iterations to finish. And the question of the next part is, can we do better? So it's about how to choose algorithms that fit to your optimization problem. So the next practice session is going to be slightly difficult, but exactly what you will find in practice. You get starter code from us doing 2 optimizations, 2 different criterion functions. They don't actually even fail, like they don't produce an error. One even says success equals true, but they will not produce the right result. And then you have to find a way to use different algorithm or different algorithm options to make it work. So picking algorithms has two components. One is the more theoretical one that gives you a first selection of candidates, and then the more practical one. The theoretical one, like we abbreviate this a lot, is basically based on the properties of your function that you have to know. So one of them is smoothness. Usually people only decide between differentiable and non-differentiable, but it does actually make a huge difference. Like, is it maybe differentiable almost everywhere but has some kinks, then you don't have a problem. Discontinuities and flat spots, a bit larger problem, but depends on the optimizer. And if it's stochastic, it becomes really difficult. Another important property is convexity. So it's mainly the questions, are there local optima? And that's closely related to your goal. So if there are local optima, are you satisfied with finding any one of them, or do you actually want the best? So do you need a global or local solution? And also, to which precision do you need it? I mean, maybe most people don't think so much about it, but you cannot really ask to do numerical optimization and get 15 digits of precision. So you should really think about what you need, and different algorithms might give you different precision. Another important question is the size. So do you have 2 parameters, 10, 100, 1,000, maybe much more? It really drastically changes which optimizer is going to work. And it's not like any optimizer that's really good for 1,000 plus parameters would also solve the smaller problems. It really depends. Another question, which is typically a hard constraint, are constraints. Some optimizers can handle them, others can't. Estimagic tries to do a bit about it, but general nonlinear constraints are only supported with some optimizers. Another topic is, does your function maybe have some special properties, some special structure? So in many estimation or data fitting problems, you have so-called nonlinear least square structure, where you have some multiple functions and then basically square them and sum them up. If so, then you can actually exploit this and it will help you. But I'm going to show this a more formal definition of this later. And as I already said, both properties guide the selection, but then typically you come up with 2, 3, 4 candidates. And the best thing is to actually just try out which one works best. You don't have to do a full optimization for that. You can set like very strict stopping criteria, look at a convergence plot and see which one goes fastest. So now I'm going to present a few of the algorithms that are supported in Estimagic. There are many more. And actually, these slides are mostly meant for you as a help during the next practice session. So I'm not going to talk about all the points even, but just highlight the most important ones. So one that you've already seen in the examples is scipy LBFGSB. So this limited memory BFGS algorithm that supports bounds. BFGS is a method to generate second-order derivative information from multiple gradients, basically. And it's a very widely used method. So many algorithms use this. For this to work, the criterion function must be differentiable. If you have a few kinks, that's okay, but if it's really noisy or has discontinuities, it won't work. This algorithm scales well up to a few thousand parameters, but of course we're not going to do that in the examples because it will take longer then. And this particular implementation of BFGS speeds in benchmarks, we have run many other implementations. So there's the just BFGS in scipy, there's the BFGS in NLOpt, but this one is actually really good and I use it a lot in practice. FIDES is a not very well-known algorithm. It's actually a standalone Python package that we wrap. It's a derivative-based trust region algorithm, has similar use cases as LBFGSB, but it actually works better in cases where LBFGSB is too aggressive. So sometimes if your code is numerically unstable, LBFGSB usually will find it in the second or third iteration. And with FIDES, you have a few advanced options that you can set, like the initial trust region radius that limits that a bit. Yeah, both of them are used a lot in practice. NLOpt Bobika and NUC Bobika are two gradient-free optimizers, so they should implement the same basic optimizers, but the implementation varies a bit. In general, the NLOpt version has less overhead, so if you have a very fast criterion function, you should choose that. And one from the numerical algorithms group has advanced options to deal with noise, and also, I mean, it's not going to make it a global algorithm, but it gets a bit there. And in general, these algorithms are going to be slower than gradient-based algorithms, especially if you have fast derivatives. But they are going to be faster than the next one. But no presentation about optimization would be complete without Nelder-Mead. So the Nelder-Mead algorithm is a very, very popular algorithm from the 60s, I think. It's a direct search method. That means that given the current parameter vector, it evaluates the function at a fixed pattern around this current point in each direction. And then it simply takes the best one as next parameter vector. And that makes it relatively robust because it only looks at the order of the function evaluations and not the exact values. But it is almost never the best choice. So very popular, but typically the previous ones are going to do better. Then we have two nonlinear least squares algorithms. Both are derivative-based. But let me first define what a least squares problem is. So if you have your criterion function f of x, then in a least squares problem, it is actually made up out of the squared, summing the squared terms from a vector, from several functions fi of x. So each of these fi of x returns a scalar. You can stack them into a vector and you get your so-called least squares residuals. And if you want to use a least squares optimizer in Estimagic, your criterion function should not return just the scalar value, but actually a dictionary that contains the least squares residuals under the key root contributions and the value separately. Actually, you can omit the value if you want. Examples of this are many data fitting problems. So if you have, for example, simulation models that, let's say I've worked on a COVID model, so we were predicting COVID infections, and then we wanted to fit them to real infections. And what we actually fit was the squared difference of real and simulated infections. Yeah. So the documentation on these states that LSLM is better for small problems without bounds and LSTRF better for large problems, but they actually both work very well. Yeah. And then NUC, DFOLS, and pounders are basically the derivative-free version of that. So they also only work if you have the least square structure, but they don't use gradient information. Instead, they fit a surrogate model of your function, of your criterion function, and then use the gradient of that surrogate model. And this is in general better than using the derivative-based ones with numerical derivatives. But if you can have access to like closed form derivatives that are really fast to evaluate, then you should use one of these. Finally, IP.opt. I have not much to say about it. It's just the best open source optimizer for large problems with many nonlinear constraints. I think there are even better closed source optimizers, and we're working on supporting them in case you have a license. But currently they are not supported, so this would be my go-to choice for constraint problems. But more on that later. We have a question? Yes?
Can you talk about which closed source optimizer you're currently working on?
So for a constraint problem specifically, we want to support SNOpt and Nitro. But actually, like if you want a particular optimizer support, whether it's open source or not, make an issue, and we're going to work on it. It's actually really easy. So typically supporting an optimizer is half a day of work at most. Do we have more questions? Okay. Okay. Then we already get to the next practice session, the third notebook. As I said, you get code snippets for with criterion functions, and we also add the code for running the optimization. It does not give you an error message, but it does not produce the correct result. And one hint is that maybe look at the first line of the first function. So there we are doing some rounding, and that introduces a problem. So one more thing for those who are done quickly or so, or maybe have a specific favorite algorithm that they want to try out, you can go to the documentation, and here you see the list of all optimizers grouped by the packages from which they come, and you can try out all of them. Yeah, so that works. So maybe one note on this. So we import available algorithms here because we don't want to force you to install all those packages. So in your environment, you have most of the algorithms that we support. But in practice, you can choose if you want to install NLOpt and all the other optional packages.
Okay, let's start and discuss the solution for the third exercise sheet. Now, I guess you've all read the problem description. So, as Janos already alluded to, in the definition of the Powell steps function, in the first line, we introduced this tiny bit. So we round the input vector, and we will see what that does to the optimization. So the first task was to understand why the algorithm LBF GSB got stuck at the start parameters. And we already talked about that this algorithm uses gradient information, but when we round the input vector, of course, at any given point, the gradient is 0. So it thinks it terminated because the gradient is 0, but of course it didn't. So it's stuck at the start parameters. Now, the other task was to find another algorithm that converges to the optimum. In this case, when you understand the function, that it is a step function, and that the gradient information is of no use, you can of course use an algorithm that does not use the gradient information. So this is what we do here. We use a gradient-free optimizer, in this case NUG DFOLS. Of course, there are also other algorithms that do not use the gradient information that should have worked equivalently well. Okay. So for the second problem, we had the Bratu function. Yeah. Can you repeat the question, please?
The first one is gradient free. Which, besides the rounding, which one made it gradient free? Or was it just the rounding?
Okay, so the question is like which mate is gradient free. Maybe let me clear that up. So it's not the criterion function that's gradient free. The gradient of this criterion function is 0 almost everywhere. So just exactly at some points it has the discontinuities, and everywhere else is at 0. So then the solution was to use a gradient-free algorithm. But being gradient-free is a property of the algorithm, not of the criterion function. Yeah. And what we used is the NUG DFOLS, which does not use any gradient information. But for example, Nelder-Mead would have worked here, Bobika would have worked here, anything that does not use a gradient.
Did that clear things up? Or
I'll give it.
Yeah, I can also come to your place at the beginning of the next exercise section and we discuss it.
okay. So for the second problem, we have the Bratu function. And the task was to understand why the scipy.optimize function algorithm here did not converge on this problem, and then find a better solution or a better algorithm. So first question is, of course, why do we know that it did not converge? So we should have known the starting, or we know the optimal criterion value. This is what we gave here. And we know the criterion value from the result of the optimization, so it's not 0. If we did not know that the optimal criterion value would be 0, we could still imagine that we saw a change from point 15 to point 14. So in a real-world application, we wouldn't have known that it did not converge. Yeah. And of course, we have our Estimagic criterions, and we do not have any stars here. So do not believe that all the time, but in this case, it's correct. So if we would have seen some stars here, like p-value stars, then would have believed that it converged, but it did not have no stars. So first of all, this problem, it's a bit more difficult, and the Nelder-Mead algorithm does not, as we've seen, does not use any gradient information. So one step would be to use an algorithm that uses the gradient information, because in this task, or in comparison to the first task, we can use the gradient information. So we can just try out the scipy LBF GSB algorithm. And when we look at the minimization result here, we see that the criterion improved to nearly 0. So that's a lot better. But we could have also looked at the criterion plots and compared the two algorithms. So maybe some of you already did that. So I'm going to show you that. So first we minimize with scipy and Nelder-Mead. And we need that. This won't work. And now, as you've already seen, we can use the criterion plot. And we have like Nelder-Mead. And we had LBF GSB. Now we can look at the criterion plot. And well, I mean, what you can see is that the LBF GSP algorithm converged pretty quickly, and the Nelder meet kind of got stuck. And one nice feature of these asymmetric plots are they are done with Plotly, so you can zoom in when you have a notebook. So maybe zoom in here. And then we realize that, yeah, the LBF GSP algorithm converged pretty quickly, but the other one did not. Okay, but again, I mean, there are very different ways to solve this problem. You can also use different algorithms, so many valid solutions. So are there any questions to the second task, or also to the first task?
Do you see the function like returns large and value and just drops? Is that why you can't use a gradient?
Here again, so because of the rounding, it introduces like a step function behavior. So we have constant values for certain areas. And because the criterion value is constant in these areas, the gradient, of course, is a 0. And then you have these discontinuities. So this is why the rounding introduces a step function-like behavior. And of course, step functions, they have like a gradient of 0.
So maybe let me illustrate a bit more. Let's say we had a very simple parabola that we wanted to optimize. And now we introduce the rounding, so then the function would stay constant for everything that gets rounded down to this value, then drop, and then stay constant again. So what you have in the end is a bunch of step functions, and then the gradient information is not useful because it's actually 0 almost everywhere except here. If you're using numerical gradients, one option is to increase the step size if you have that problem, but there are usually better options. Okay, so maybe those who have finished early and tried out many algorithms, or I saw some of you looping over all algorithms, did you try out which one is the best? Okay, yeah, that's what I would expect. Like from looping over 50 algorithms, you probably have some global ones that take quite long to run. Yeah. LM, yeah. That would actually be expected because it's like a least squares problem, and it's a derivative-based least squares algorithm, and it's differentiable. So, yeah. Sounds exact. Yeah, sounds right. Yes.
Do we have any kind of a grid search function to find the best algorithm? Going one by one.
A grid search to find it. So the question was: is there a grid search to find the best algorithm? We haven't implemented that, but the next topic is actually benchmarking, and this is probably the better way of addressing this. Okay, then we continue. Actually, I could not have asked for a better introduction to benchmarking than this question. Thanks a lot. So yeah, in preview of the next practice session, you're going to run benchmarks. So you compare different optimizers on a set of benchmark problems, and then you visualize the comparison using profile plots and convergence plots. What is benchmarking? Benchmarking means that you compare algorithms on a set of functions that have a known optimum. So you know the optimal function value and the optimal parameters. And this can be used to find out which optimizer is in general good for your kind of problem. For that to work, the benchmark problems actually need to mirror the problem you actually want to solve. So they should have a similar number of parameters. They should be similar with respect to differentiability or noise. If you have a badly scaled problem, they should also be badly scaled, and so on. And the key difference is that benchmark functions should be fast. So you can try out many algorithms on many problems and then select which one is best. If you used your real function, which probably takes much longer to evaluate, then running the benchmark would take forever. So running benchmarks in Estimagic has 3 simple steps. The first one is you get a problem. The second is you define which optimizers you want to benchmark. And the third one is actually running the benchmark. So to create the test problem set, you can simply choose different names. So we have an Estimagic benchmark suite, which just covers a large range of different sizes and different function properties. And then there are some more specialized benchmark sets. We are working on having more benchmark functions and want to at least implement all of the standard sets from the literature. And you don't really have to understand like the format in which the benchmark problems are stored. It's a dictionary having the functions and some information, but you're usually not going to modify this manually. You're just passing it to some other functions. Then for simple benchmarks, you can define a list of optimizers. For a more advanced benchmark, you can pass any kind of optional keyword argument to maximize and minimize also via this. So you can compare the same optimizer using different tuning parameters, for example, or something like that. And then finally, running the actual benchmark, you pass it the problems and the optimize options. You should set the maximum number of criterion evaluations not too high, because this is going to take some time. And finally, you can parallelize it. So if you have multiple cores on your laptop, which most of you are going to have, you can set this to an appropriate number, something between 4 and 8 typically. Now, just having these results would not be very useful. What we actually want are plots. So I show you 2 standard ways of plotting benchmark results. The first one is a so-called profile plot. So on the x-axis, you have the number of function evaluations it took. And on the y-axis, you have the share of problems solved. So remember, a benchmark problem set has multiple functions. So the Estimagic set has, for example, about 30 functions. And even our smallest one has 8 functions. And then simply we look at over time which share of these functions has been successfully optimized. And then you see, for example, that scipy LBFGSB, it either works or it doesn't. So if it works really fast, but then it doesn't make any more progress. And other optimizers are a bit more robust. So the DFOLS is, for example, slightly slower, but it gets actually higher. There are also some, like just because an optimizer is slow doesn't mean it's robust. The Nelder-Mead optimizer, for example, is rather slow and doesn't solve many problems. But of course, this statement is like contingent on this specific set of problems, which is rather varied. We could easily find a set that has only non-differentiable functions, and then LBFGSB would not solve a single one of them. So it's really only for this specific set of problems. And then if you want to zoom in a bit, you can look at convergence plots. So this, for this, usually it's good to define a subset of the problems that you want to look at, because otherwise we would have to look at 30 plots. And then you can check, like for each optimizer, if they solved it, and if so, how fast. Actually, all of these plots have many optional arguments, so you can set, if you want to measure the runtime in function evaluations or in actual wall time, you can check how precisely do you have to get to the optimum to count it as success and all that kind of stuff. But typically it's already quite informative to just use the defaults. There was a question?
Yeah, I just want to clarify what is the number of function evaluations. So like in this graph, you have share of problem solved, so it's like 8, like, so it's like 49, it's like 80% of.
Yeah. So
What is X for X?
in this benchmark set, we have, I think, 30 functions. And then we run them with 4 different optimizers. Now, the number of function evaluations we count separately for each problem that is going to be solved. How often did the optimizer evaluate the criterion function of that optimization problem? So this is basically measuring the runtime, because if you have a slow criterion function, the criterion evaluations completely dominate the runtime of the optimization.
Does that number include the evaluations for gradients?
Good question. So this does not include the number for numerical gradients. If you want to count that, you have to multiply by n, basically, by the number of parameters. And that would change it differently. But I mean, as a tendency, you would only use a gradient-based algorithm if you have closed-form gradients in most real applications, at least if you care about the runtime. That's why we don't count them here. But it's a good question. So if you're really interested in that, you have to multiply by n. Are there more questions? Okay. So then quickly, why do we look at runtime? So each of these benchmark functions, as I said, they should be fast, takes at most a few microseconds to evaluate once. And then the runtime of this is completely dominated by the algorithm overhead. So we have a few pure Python algorithms that would look really bad if we looked at runtime. But actually, if in real applications, most criterion functions that I work with take actually a few minutes. So in that case, you completely don't care about algorithm overhead. But it depends on the use case, and if you're in the situation where you care about the overhead, you should use runtime in the plots. Okay, then we come to the next exercise to run a benchmark, basically repeat the steps that I showed you in the slides. If you have a very slow laptop, maybe always use the example benchmark suite instead of Estimagic, because it has much fewer problems, and don't use too many algorithms. Yes? Sure, I'll come.
So let's start with discussing the fourth exercise sheet, which was about benchmarking. Now you were given the example benchmark problem set, and we had 4 optimizers, and there was a typo here. Actually, probably most of you noticed that S shouldn't have been there. Actually, in the solution it's correct. In the problem description, we had a problem that there was a B, an extra B. So task 1 asks you to run the benchmark and then plot the results using the profile plot. So running the benchmark, you use Estimagic's run benchmark function with the problems, and you set the optimize options to the optimizers you want to use. Now here I use warnings, or the warnings catch warnings filter, and many of you notice that if you don't do that, you get a lot of warnings that an opt also did not converge or had a problem through an error. And this is actually intended, so you probably also realize that these are just warnings. So the benchmark still runs through. You don't get a proper error. And we actually want that, because for the benchmark, it's also important to realize if an algorithm fails. And we just count that as the algorithm not terminating or not successfully terminating. So now we've run the benchmark, we got our benchmark results. We can just put that in the profile plot with the problems, and it should look something like that. And from here you can see that the NLOpt LBFGS did not really work that well. In the warnings, you should have seen that also, because you got a lot of warnings that NLOpt did not converge or through an error. And the fetus and the NUC DFOLS, they did pretty well. So in task 2, we should switch to the Estimagic problem set instead of the example problem set. And now we should also set the number of cores, because if you have a lot of cores, then it might be a good idea to use those and parallelize the benchmark, which is just faster. As on top of that, because it's so interesting, we wanted you to realize that different implementations of the same algorithm might perform very different. So we compare the scipy NLDAMeat with the NLOpt NLDAMeat. So again, we load the problems with the Estimagic problem set, choose the two NLDAMeat optimizers, and run the benchmark. Also setting the number of cores to 2. And here I didn't catch the warnings, so this is probably what you have seen. Now, if we consider the profile plot, we realize that the NLOpt NLDAMeat, the NLOpt implementation of NLDAMeat, just performs better. It just dominates the scipy NLDAMeat. It's an interesting observation. And now going to the convergence plots. So we're going to look at the individual functions. We see also that basically for every function, the NLOpt NLDAMeat just converged much quicker. Yeah. So if you have any questions, or do you have any questions? Yes.
Just why?
Sorry?
Why is that? So the same algorithm that you're implementing, why does that happen?
So I actually don't know exactly why. Otherwise, I would have made a issue. So the NLDAMeat algorithm has multiple different implementation for like how to initialize the simplex and stuff like that. So I guess they just chose one that works better for most problems, but I don't know what it is. And I mean, the goal of this is not to trash the scipy version, but maybe to make you aware that you should not implement your own optimizer unless you really know what you're doing and are really prepared to compare it to all existing implementations. So, yeah.
Any other questions? Yes.
So just a follow-up to that, so maybe even internally setting the seed differently in the scipy version of the implementation for the algorithm that could change the result.
So I don't think that there's randomness in the NLDAMeat algorithm, but for other algorithms this would apply. So the question was, could this even be related to seeds or so? So this was a very robust finding across many different benchmark sets. So it seems just like, I would expect it's like the initial simplex size or something like that. There are different methods. And I'm going to try to reverse engineer what goes wrong or look at it, but I haven't really looked into it. I'm also not an expert for that.
Okay, so if there aren't any other questions, then we have a 10-minute break now.
Okay, then we continue. First of all, I want to say it makes us really happy to see how concentrated you work on all the exercises, especially given that this is already the second day and the second tutorial today. So really nice. Okay, let's talk about bounds and constraints. So in the practice session, you're going to solve an optimization problem where you set bounds on the parameters, you fix some of the parameters at their start value, and you also use linear constraints. And in the code snippets, I'm also going to show you how to use nonlinear constraints, but you're not going to do it in the tutorial. But first, let's look at bounds. So we have them in this chapter, in this section, because they are also some kind sometimes called box constraints, but they're actually rather different from how other constraints are implemented. So they're simply lower and upper bounds on parameters. Let's say you have 5 parameters, then you could say the first one needs to be larger than 5. That would be a lower bound. Bounds are not handled by all algorithms, but by many. So in, I think all NL-opt algorithms handle bounds. In scipy, not too many algorithms handle bounds. But if you look at all algorithms in Estimagic, then you see that most of them handle bounds. If they don't, we cannot do anything about it, but you will get an error message. Very importantly, the bounds need to hold for start parameters, and they are usually guaranteed to be fulfilled during the whole optimization. This is very important if, let's say, you want to estimate a variance, and if it's negative, you cannot work with it. It would even be undefined. So they are guaranteed to be fulfilled. And how you specify them depends on how you specified your parameters. So for the very simple case of your parameters being a one-dimensional NumPy array, you simply use the lower bounds and upper bounds arguments to minimize. You can use both of them or just one, and pass also a 1D NumPy array of the same length as your parameter vector. And if the bounds don't apply to all the parameters, you can use minus np.inf and np.inf or nans to say that this specific parameter has no upper or lower bound. If you have your parameters in a data frame, you can bundle the bounds and the values together. So the value column of that data frame contains the parameters you're optimizing over, and the lower bound and upper bound column contain the bounds. And again, you can use nans or infs to specify that some parameter has no bound. And finally, if you have a dictionary, or what we call a pi tree, because it's even more general than a dictionary of parameters, then you need a matching pi tree for the bounds. Now, there's a special thing that as long as there's no ambiguity introduced, we try to match, if you specify a smaller dictionary of bounds, try to match it with the larger dictionary, or even for nested dictionaries. So in this case, for example, where we have two entries in the dictionary, x and intercept, and we only want to specify a bound for the intercept, you can do that. You can leave out the x. You don't have to put minus infs or so. And of course, like if it's ambiguous, for example, if you had a list of arrays and your list of bounds is too short, also you get an error. Then let's talk about constraints. So constraints are conditions on the parameter vector, and they are not simple bounds in the sense that they could be nonlinear, or they could introduce some weighting, or in general the bound that are induced on parameters by, or the restrictions that are induced on one parameter may depend on some other parameter. So we might have linear constraints. They could be of the type AX is between L and U. There could also be a linear equality constraint, so AX equals V can also be combined. And then there are nonlinear constraints. There are simply constraints of type C1 of x equals 0, and C2 of x is larger or equal to 0. Actually, here you can also provide lower and upper bounds, but you're going to see the syntax later. And finally, Estimagic has some specialized shortcut constraints. For example, for finding valid probabilities, i.e. numbers between 0 and 1, summing up to 1, or finding valid covariance matrices, as these come up very often in estimation problems. And actually, the constraints that Estimagic implements work with almost all optimizers. So let's look next at an example and find some valid probabilities. We again use for simplicity the sphere function that we've used so many times before. And the start parameters now, we want to say that the first three parameters should be valid probabilities, so non-negative, smaller than 1, and sum up to 1. And this also holds in our start parameters here. And how you would specify it is you pass a list of dictionaries, or in that case, if there's just one constraint, a simple dictionary where the location, the log entry specifies which parameters are involved in that constraint. And the type parameters specify which type of constraint it is. And here you can have all the shortcut constraints that are implemented in Estimagic. And when you run the optimization, you'll see that it actually works. So these are all valid probabilities. The LBFGSB optimizer is unconstrained. So question is what happened. Estimagic can implement some of these constraints via reparameterization. So instead of searching over the original parameter space, we transform the parameter space and search over one where, by just obeying bounds, we actually also obey the constraints. And this basically transforms a constrained problem into an unconstrained one, and then passes that unconstrained problem to the optimizer and does all the conversions back as well. And maybe many of you have done optimization previously, have implemented this manually. It's something that, like in economics at least, that's like what's passed on in the labs, like different tricks to do the reparameterization. Importantly for this approach, the constraints also need to hold in the start parameters, because otherwise you cannot convert the start parameters to their equivalent in the converted space. And then the benefit is they also are guaranteed to hold during the entire optimization, which is good for exactly the types we have implemented. Let's say a covariance matrix that needs to be valid because you want to sample from it, or probabilities that you also use for sampling, they need to be actually valid. So which constraints can we handle that way? The most simple one that doesn't even count as a constraint is fixing parameters, finding valid covariance matrices or correlation matrices, finding probabilities, but also general nonlinear constraints can be general linear constraints can be implemented that way, as long as you don't have too many. So you cannot have more constraints than involved parameters. Otherwise, some rank condition is not fulfilled. And if you want to read up on how this is implemented, we have a long section in documentation in the explanation section. But actually, the goal was that you don't have to know how to use it, because we implemented it once. Okay, now we look at a few examples of constraints, and then you're going to continue with the next exercise. So here we want to simply, yes?
What does it mean, not too many?
So not too many means you don't have more constraints than involved parameters. Because otherwise, so you need to invert a matrix that in that case is square, but otherwise wouldn't be. Yeah.
You have to sort of figure out which constraints are superfluous or redundant.
We do some of that, but we don't do a good job on that. So especially for inequality constraint, this is a quite hard problem. And we just do some, like if you have really redundant constraints, we are going to drop them. But it would actually be nice to maybe use scipy to get much better at that. But the rule of thumb is, like, if you really have too many constraints for that, then use a constraint optimizer and we pass them on. It's currently not implemented for linear constraints, but for nonlinear ones. Yeah. But also, if you have a good idea of identifying redundant constraints, let me know and we can work on it. Okay, so here we simply fix a few parameters. This criterion function we are going to use for all examples that follow. So it's basically the sphere, but it has some offset. And then the unconstrained optimum is actually 1, 0.8, 0.6, and so on up to 0. And now we have the start parameters, 2.5, 1s, and then minus 2.5. In the log field of the constraint, we select position 0, this one, and 5, which is this one, and then say type equals fixed. And running the optimization, we actually get that. So since this is additively separable, the other parameters don't change, so they don't get affected by the constraints, but the first and the last are fixed. And this is just useful if you have a very difficult optimization, maybe for the start parameters. Maybe you have good start parameters for some values, then you want to fix them there and let the optimizer find better values for other parameters and so on. And then you can iteratively free parameters. Linear constraints are the type AX equals B or inequality constraints on that. And so here we want to impose the constraint that the first 4 parameters have an average that is larger than 0.95. And we do that again by selecting the first parameters using log, setting the type to linear, and then lower bound and weights. The weights can be a scalar or they can match the selected parameters. This is the result. Very important, again, for this type of approach to constraints is they need to hold in the start parameters. And if not, then you get this error that reminds you to fix that. So here the first 3 should be probabilities, but they don't sum to 1, and then we even find that in the error message. Nonlinear constraints are very different from that. So this type of constraint works for all optimizers that support bounds. Nonlinear constraints only work for optimizers that actually support nonlinear constraints. An example of that is scipy /qp. We also had scipy.optimize, which is really, really good. And we are working on support for more constraint optimizers. So here what we do is we restrict the product of the first 5 parameters to 1. And we do that by selecting parameters again, the first 5, type equals nonlinear. The function implements the actual nonlinear part of the constraint, and then the value is 1. If you have an inequality constraint, let's say you wanted this to be larger than 1, then you would remove the value entry and add lower bound equals 1. And what we are doing with these constraints is simply we converted them to the different kinds of interfaces. So scipy has a different interface for nonlinear constraints than IP-opt. We convert them and pass them on to the optimizer. There are other options to select parameters, and they depend a bit on how you specify the parameters. So you saw that in each of these constraints, we used a log field that told us which parameters are involved in this constraint. But if you don't use a NumPy array, there are actually usually better ways than doing the positional indexing for that. So if your parameters are a data frame with value column, as we've already seen, you can, for example, use a query on that data frame. You can have any number of additional columns. We don't look at them, but you can use them in the query. Or you can use the log field, but in this case, it's not a positional indexing, but a label-based indexing into the data frame or into the series. And finally, for the most general case, let's say you have a very deeply nested dictionary or so, you can use the selector function, which is the same as in the params plot that you've already seen. So you take any subset of the parameters out. And actually what you take out can again be a dictionary or whatever, and we flatten it. So we are currently not using this, but requiring to select subsets for nonlinear constraints will also help us to discover sparsity patterns in the constraints, which can be used to gain some efficiency. If you want to know more about the types of supported constraints, you can look at the documentation. It has detailed examples for each of them. If there are no further questions, then we will go to the next practice session, which where you will use a few simple constraints and bounds to solve the problem you already know. So actually in this notebook, if you pulled yesterday, we have a small change. So the exponent here is, I think, 4. It doesn't really change the optimum. It makes the problem more difficult, and because you have a very flat spot around the optimum, that's why we changed it to 2. But actually both of them work. In the solution, we are going to show exponent 2.
Yeah, and for the second and third term, we just use the linear norm and don't square it. So you need to square it as well. Just use that code.
You can simply copy the function that you had in previous exercises.
Okay, so let's start discussing the 5th exercise sheet for bounds and constraints. So we first introduced the example which we also had in the previous exercises, the sphere criterion function with like the dictionary parameters. We have our start parameters. And yeah, for illustrative purposes, we also run the minimization again without constraints. Now, the first task is to set bounds. And it asks us to set like an upper bound of 2 for the parameter A and a lower bound of 0.5 for all the entries in B. So how do we do that? We can simply pass additional arguments to the minimize function of Estimagic, one being lower bounds, where we have a subset of the whole parameter dictionary. Because we only want the lower bound for B, we can just use the key B, and then we have 0.5 times numpy ones like, so that we get the correct size of the array. And for the upper bound, it's a scalar, so it's a bit more simple. We just have, again, like a sub-dictionary of the whole params dictionary, just say A and 2.0. So we have an upper bound of 2. Now for task 2, we were not supposed to set bounds, but fix parameters. In that case, we should fix the parameter A, as well as the top right entry of C, to their starting values. And this is now a proper constraint and not a bound anymore. And we've seen that constraints we implement as a list. Now we have a list of 2 constraints. So the first constraint is just a fix, so the type is fixed, as it's asked in the question. And to select it, we cannot use a lock. We need a selector function because the params, or the start params, those are a general pi tree. So we need our selector function, which is in this case just a lambda function, which takes the params. So this x represents the params, and we select the A using the key A. Similarly, for the second fixed constraints, we knew that x of C is a matrix, but we only want the 0, 1th entry, so we do that as well. And when we do that, it works out perfectly. Because of time constraints, we will skip the optional part, but if you want to discuss it, we can do that later.
There's a question on this solution that Dot has here that works with the constraints of just one dictionary, and then the lambda expression is listed by the lambda that has the symbol XA, comma. Yeah, and you see, so we set both in one lambda expression and we got the correct.
Yeah, so this is also a possible solution, yes. So you could also, what you described.
Which one would be preferable?
It would be exactly the same. So we harmonize, like basically no matter how you specify these constraints, if they imply the same, they will be numerically exactly the same solution. The optimizer is going to see exactly the same transform problem.
So wait, before we start, are there any other questions? Perfect. Well, then.
Okay. Then let's talk about global optimization. This is the only section on which we don't have a practice session. The main reason is that if we, like all the interesting examples we found would have taken too long to run, and all the others would maybe have given you insights that don't hold generally. What is global optimization? So far, we've mainly found local optima. Most of the functions, for most of the functions we had, they were convex, so this was the same as global optimization. In general, global optimization means we don't just want to converge to any local optimum, but to the best one. And a global optimization problem needs bounds on all parameters to be well specified, because otherwise, we could just not guarantee that there's any global solution if we can't restrict the parameter space. Doing global optimization becomes extremely challenging in high dimension, and high actually starts at 5 or so. Even for not too huge parameter vectors, finding a global optimum of a general function is not an easy problem. So let's look at two examples. They are both functions that have multiple optima, and we might want to find the best one of it. They are very different. So the left one, for example, has just a few deep valleys. The right one is rather rugged and has really, really many local optima. And these properties do influence which approach to global optimization you want to choose. So first question is maybe how about brute force? Can we simply do a grid search? But it actually doesn't work for more than a handful of dimensions. So the right table shows you the numbers of dimensions in the first column and the runtime in the second column, the runtime of a grid search in the second column. And the assumptions behind this calculation was that each function evaluation takes 1 millisecond, which is not very much. And you want 100 points per dimension. So for example, if you had bound 0, 1, this would give you 2 digits of accuracy, which is also not that much. And then for 1, 2 dimensions, it works well. For 3, you could do it. But starting 4, 5, and 6 dimensions, it becomes really difficult. And the reason is the curse of dimensionality. So if you add more grid points, add more dimensions, the number of grid points you need does not scale linearly, but exponentially. So now I want to introduce 3 broad approaches to global optimization that try to do better than grid search. The first of them is genetic algorithms. So those are heuristics that are inspired by natural selection. And typically these algorithms start with a random initial population of parameters. So they sample parameter vectors from within the bounds. And then in each evolution step, they evaluate the fitness of each parameter vector, which is just the criterion value. And then they discard the worst entries from the population and replace them by combination of good entries. And combinations means typically some kind of convex combinations of the parameter vectors. And usually these algorithms converge when some kind of max iterations is reached. So it's not like local algorithms that they have nice stopping criteria based on gradients or so. And examples for these algorithms, we have actually quite many in the PyCmo, from the PyCmo library, but also NLOpt has a few, so you can check out the documentation. And some of these can do the criterion evaluations in parallel. Another approach is Bayesian optimization. So what this does is it also starts by evaluating criterion function on some kind of grid and then builds a surrogate model to your criterion function. So it basically estimates a regression model to your criterion function over the parameter space. And you've heard of trust region algorithms before, local optimizers. So what they do, they build surrogate models in the vicinity of the current best parameter vector. Bayesian optimizers build a surrogate model over the entire parameter space, which is much more difficult. And then in each iteration, they do new criterion evaluations at promising points in the parameter space. and also use those points to refine the surrogate model. And over time, the surrogate model becomes better and better. And there are many different ways of fitting these surrogate models, but that's the general approach. And they also typically converge after a fixed number of refinement steps or so. And finally, there's multi-start optimization. Now, there are different ways of doing multi-start. I'm presenting the one that's implemented in Estimagic. So we first also evaluate the criterion function on a random exploration sample. You can choose different sampling methods for that. Then run the first local optimization from the best point of the exploration sample. And then in each iteration, we combine the currently best parameter, so this is usually the result of a local optimization, with the next best exploration point, in a similar way as the genetic optimizers combine good parameter vectors. And then run a local optimization from there. And this multi-start approach converges if the current best optimum is rediscovered multiple times. But otherwise, you can also let it converge after fixed numbers of iterations. So let me show an example. So first of all, I want to say that we did not come up with this multi-start algorithm. It's inspired by the tic-tac algorithm, and this link shows you to a Fortran. This link goes to a Fortran code repository that implements this kind of algorithm. So you can use it by basically you do the optimization as before. You provide soft lower bounds and soft upper bounds in the same ways as you have seen how we can provide bounds. And those are used for sampling, but not during the optimization. So that's a way of not being too restrictive and only use the bounds for the start parameters. Then you set multi-start to true. And if you want, you can provide a bunch of multi-start options. So it's basically which sampling method do you use, pure random sampling or some low discrepancy sequence, which distribution you want, after how many rediscoveries you want to converge and stuff like that. And of course, in this simple example, it each of the local optimizations finds the global optimum. So how would you choose between the three approaches? This is actually just a very rough rule of thumb here. So if you have extremely expensive criterion evaluations where you can only do a handful, then typically Bayesian optimization works well. Bayesian optimization does not work too well if you can do many criterion evaluations, because some of the Bayesian surrogate models actually take a lot of time to fit if you have many criterion evaluations, if you have many data points. If you have, in principle, a rather well-behaved function, let's say a differentiable function, or, for example, a nonlinear least squares function for which you have a good local optimizer that can actually make progress, but then might get stuck in one local optimum, then multi-start is usually the best thing you can do, and it really outperforms the other approaches because it only has to sample a point in the right valley, so to speak, and then the local optimizer does the rest of the work. It doesn't have to hit the right point. And finally, if you have a not so nice function that's very rugged and maybe even local optimization is challenging and it gets stuck at the start values, then you want to use a genetic optimizer typically. And in principle, all of these are parallelizable to roughly the same extent. If not, then this is a question of implementation, not really of the approach. But some of the genetic optimizers and the multi-start approach are parallelizable in Estimagic. Okay. As I said, we don't have an exercise session, and continue with the next section on which you will have an exercise. Are there questions? So?
Are there any good articles online walking through examples of what you went through?
So I don't know one source. There's a package on Bayesian optimization, which has a really good visualization of that. For genetic algorithms, I don't really know But the PyCmo documentation has someone on it. Yeah. But if you don't find anything, you can text me on Slack and I'll look for it. And yeah, and by the way, so the problem was we couldn't find any very simple example where multi-start didn't just extremely outperform the others, because for most of these benchmark functions, they are differentiable, so multi-start is the thing to do. But this does not hold in general. Okay, so in this section, we want to talk about the scaling of optimization problems. You will first learn what we mean by a badly scaled optimization problem, then how to visualize whether you have one, and finally what to do about it. The scaling of optimization problems is a very underrated topic, I would say. I think most people who develop algorithms will think the users know about this and they will scale their optimization problem well. And most users will think that if it was important, then the algorithm would do it. In general, what we mean by bad scaling is that, or by well-scaled problems, we mean that a fixed step in any parameter direction will give you a roughly proportional change in the criterion value. It doesn't have to be like exactly the same, but should be a similar order of magnitude. Factor of 10 is even okay. And badly scaled would be if you have one parameter, like A here, that is extremely influential and completely dominates the criterion value, and one that is not. And this often arises in practice if you have very different units. For example, as economists, we might want to find an optimal consumption bundle containing houses and cups of coffee, where, of course, you have many cups of coffee and they are cheap and they don't influence the cost, and houses are expensive and you have just one of them. So I want to show you the empirical effect of bad scaling. For that, I will use the standard Estimagic set of benchmark problems, a badly scaled version thereof, and a badly scaled version, but we set scaling equals true in Estimagic and let it do its magic. So this is how I called get benchmark problems for the plots that you're going to see now. We set scaling equals true, and the scaling options are min scale 1 and max scale 1000. So this means that compared to the original problem, the first parameter vector gets multiplied by first parameter entry gets multiplied by 1, the last one by 1000, and the rest by a lin space between those two numbers. So the difference is 3 orders of magnitude. And then if we look at the LBFGSB algorithm, for example, which is gradient-based, so typically gradient-based algorithms are less scale sensitive than gradient-free ones. It does make a difference. So in the badly scaled problems take much longer to solve, but actually the algorithm solves most of them. And setting scaling equals true, which rescales the parameter space by the start parameters by default, almost solves this problem. More importantly, if we use NUG-DFOLS, for example, it does not get slower, it actually solves fewer problems. So this is really a problem. And I know multiple people who have spent more than a month of their life because they did not know that the scaling matters and try to solve an optimization problem with actually the right optimizer for that problem, but not thinking about scaling, and it just didn't work. And I also want to show you one exception. This is the NL-opt-Bobica, which is not affected by scaling. And I don't know why, because this algorithm in principle, so the NUG-Bobica, for example, is affected by that. I think they just do some scaling inside the algorithm, probably. But if anyone knows, would be interesting. Okay, how do you actually use Estimagic scaling functionality? In the simplest case, you actually just set scaling to true, and that rescales with the start parameters. Exception is parameters that are very close to 0. There's some clipping value. I think it's 0.1, so we don't divide by 0. And then the parameter space that the optimize sees is x is actually a vector of ones, and the whole parameter space is scaled by dividing by x start. And in this example of the badly scaled, completely made up function, this would recover that x0 needs a large step because it has a very large start parameter. It would not recover that also the second and third parameters have very different effects on the criterion function. And a more advanced option is to rescale by bounds. So that's not the default because you don't always have bounds on all parameters. But this can be used to influence the scaling in an even better way. So if you have bounds on all parameters and set the scaling method to bounds, then we rescale the parameter space such that it is between 0 and 1 in all dimensions. And this usually works very well. And in this case, it would also recover that here we have, for the last parameter, we need very small steps. Finally, this is an overview of some of the algorithms we have seen already and divides them into very scale sensitive, somewhat scale sensitive, and not scale sensitive. Yeah, if you're working on the example, you can look at this list. Okay, then we do the practice session. Think in the interest of time, we will shorten this a bit. So maybe get started, look a bit at it, but it's okay if you don't solve all the questions. And because we do want to talk about Jax and Jaxopt later.
Okay, so we have to start already. I know most of you are probably not finished yet. However, as Janos already said, in the interest of time, we have to hurry up a little bit. Otherwise, we can't discuss Jax and Jaxopt, and those are very exciting packages. Okay, so let's start with like the scaling exercise sheet. So what you were given is a badly scaled problem from the benchmark set, from the more reviled benchmark set, and we select the Chebby quad function 6, which has like 6 parameter dimensions. The first task is to use the slice plot to visualize the criterion function. And we have to set the lower bounds as start params -1 and the upper bounds as start params +1. So this is an absolute. We add a 1 to all the dimensions. And if we look at the solution, we pass on these arguments. This is how the slice plot looks like. So we have 6 parameter inputs. So we have 6 subplots, 1 for each input dimension. And we realize that for only the first one, we see something happening on the function value. So it seems like it's very sensitive to the first one. For the other dimensions, we realize if we change the input dimension a bit, not so much happens for the function value. Now, the question is like, if we scale this correctly, will we see something different? Now, in this case, we again use the slice plot, but we set the lower and upper bounds now dependent on the start parameters. So we do kind of scaling. Now here we realize once we do that, we see something happening in all of the dimensions. So in this case, probably scaling would help our problem. Okay. Any questions so far? Good. So for task 2, we actually had to, or we were supposed to run the optimization. Now, once with scaling to false and once with scaling to true. And then we compare both of them using the criterion plot. So we run it once without the scaling and we run it once with the scaling, true. So it scales automatically by default with the start parameters. So capture the results in a dictionary and plot it with the criterion plot. And we see that the naive version without the scaling just gets stuck. But when we scale it, the algorithm actually recovers the true value. Again, optional tasks. Unfortunately, we don't have time, but if you want to discuss them later, we will make them. Any questions again? Okay, guess you all want to see the Jux and Jaxopt.
Okay, so last part. Preview of the practice sessions. You will first solve an optimization problem using Estimagic, but calculating gradients with Jux. And then solve a simple problem using Jaxopt, and finally vectorize a solver in Jux. I'm pretty sure there are people in the audience knowing more about automatic differentiation than I do, but this is the very practical essence of it. So automatic differentiation is a magic way to calculate precise derivatives of Python functions. And the most important thing is that the runtime of the gradient does actually the disadvantage of it is that the code must be written in a certain way to be compatible with the automatic differentiation framework. Numerical differentiation, on the other hand, so that works for a finite step approximation to derivatives. They are less precise, and the runtime increases linearly with the numbers of parameters. So I would not put too much emphasis on this less precise, because if well implemented, it actually works well for optimization. But of course, the problem is that the runtime increases linearly, and you cannot use it for large problems. What is Jux? Jux is actually multiple things. It's an amazing package. So one is it's a GPU accelerated replacement for NumPy. But it's also a framework for automatic differentiation. So it can calculate gradients, Jacobians, and Hessians using automatic differentiation. And it's also really has pushed the state of the art of automatic differentiation. It is also a time compiler for Python code. And if you write your code in a Jux compatible way, it can make it really, really fast. If you look at Jux in the documentation or on GitHub, it's described as composable function transformations. You will see some examples of that. But this is also what makes it really powerful, because the gradients you get back, so if you take the gradient of a function, you get a function that evaluates the gradient. You don't get just the gradient at some point. So how do you calculate derivatives using Jux? You import jux.numpy typically as JNP. You import Jux. You implement your criterion function the same way as you would in NumPy, but using the Jux NumPy. Actually, this is a simplification, so there are differences between Jux NumPy and NumPy. For example, in Jux, arrays are immutable, and if you want to modify them in place, there are some constructs that allow you to do it semantically. But yeah, for simple cases, you can just replace it. And then you use jux.grad on the sphere function to get the gradient. And as I said, this is a function that you can now evaluate at any parameter vector you want. And the result that you get is not a NumPy array, but a Jux device array, but they behave very similar except for being immutable. So how would you use this in Estimagic? So let's talk a bit more about derivatives in Estimagic in general. You can simply provide closed form derivatives using the derivative argument. So those can be gradients in the case of a scalar function, but if you have a least square functions, they would be Jacobians, the derivative. Then Estimagic will simply use that. And it's no different, like you can use the Jux gradient here or your closed form gradient, it works the same. If you don't specify a gradient, which is all we did the whole time, we will calculate numerical ones. And so far, we have not specified any options, but if you want, you can influence the step size. You can choose whether we use forward, backward, or central differences and all that kind of stuff. And you can also simply parallelize the calculation of numerical derivatives. So, for example, if you don't know how to parallelize code, don't have closed form derivatives, but you want to use a gradient-based optimizers, this is really what you should do if you have a large computer. And parallelization is, again, assuming that your criterion function is not super fast because there's some overhead. It's really efficient up to as many cores as you have parameters. Okay, now we do the practice session. So those of you who have Mac or Linux machines can actually use JAX to calculate, to get a gradient and pass that one to Estimagic. And those who are using Windows, unfortunately, JAX is not going to work. It cannot be installed. That's why you had to use the Windows environment. For you, we provide the math of the gradient, so you can implement a closed form gradient yourself. And you have about 10 minutes, I think, for the exercise.
Okay, so let's start discussing the last exercise sheet on automatic differentiation. Okay, so importantly, you realize probably that we needed to update the config of JAX to enable 64-bit precision. By default, in JAX you have 32-bit precision, but we want a bit more precision here. So task 1 was to switch to JAX. So we need to use the old code for the criterion function, just translate it. And here this amounts to just replacing NP by JNP. Of course, after importing jax.numpy as JNP. And similarly, we should not forget to do the same thing for the start parameters. So these also need to be JAX arrays. For Windows, I just realized that there is a typo in the solution. It should be NP, otherwise you get a problem. Okay, then any questions for the first task? Translation? So by default, JAX uses 32-bit precision, and sometimes you want more precision. And in this case, you have to enable that using that. And now we have 64-bit precision available in JAX. Okay, so task 2 was to compute the gradient. When we have a JAX compatible function, it's pretty easy. We just call the jax.grad on our criterion function and we get the gradient. You can also time it. And we can also JIT it using jax.jit. Now for Windows, we cannot use JAX yet. So we provided the analytical expression. And you had to implement that. It should look something like that. Importantly here, because the starting parameters, they were like a general pi tree, so a dictionary. So also the gradient has to return an object that has the same shape as the parameters. So it has to look like that. Any questions for the second task? Yes. Okay. So task 3 was then to actually minimize the criterion function using the gradient information. This is just calling minimize from Estimagic, then providing the derivative. Here we use the JITted gradient. And works fine. And then on Windows, again, we use the analytical gradient by just passing the gradient to the derivative argument. So I guess this bit wasn't too difficult. Yeah. Any questions for the third task, or again for the second task? Otherwise, we're going to continue.
Okay, now we come to the last part. We are going to actually skip the practice session on Jaxopt, but we are going to stick around a bit longer. So if anyone wants to try after the tutorial ends and wants feedback, then we can do that. So what is Jaxopt? Jaxopt is a library of optimizers written in Jax. So in many use cases, so for example, if you use Estimagic, you can JIT your function, your criterion function, and get the gradient and so on. All fine, but the actual optimizer is not implemented on GPU, and the actual optimizer could not be JITted. So if you have, if you want to do also calculations for the optimizer on a GPU, or if you want to avoid overhead between different, if you solve many similar optimization problems and don't want to have the overhead between them, then you can use Jaxopt to have just end-to-end everything written in Jax, compiled with Jax, and running on a GPU. Also, the optimization itself is differentiable in Jaxopt. So if you have an optimization problem that has some tuning parameters and you want to differentiate the solution of the optimization problem with respect to the tuning parameters, you can do that in Jaxopt. So those are the two primary use cases when you should switch from Estimagic to Jaxopt. Now, one example from economics, which is my field, and we also have one economist in the audience, would be an economic model that has many agents, and each agent solves an optimization problem, a utility maximization. And then we have a likelihood function for our economic model, where we want to estimate some parameters of the economic model. And in that case, for the many agent problems inside the model, it's actually important for the optimization to be vectorized and to be differentiable. Because when we want to calculate the gradient of the log likelihood function, we need the derivatives of all these solutions to the agent's problems. And in that case, I would, for example, use Jaxopt to solve the inner problems and Estimagic to do the actual estimation. How does it work? The interface of Jaxopt is quite different from scipy and Estimagic. So instead of having a minimize function, you import the solver. Then you define the criterion function using Jax as before. And then you create an instance of the solver, just passing it the criterion function and potentially some tuning parameters to the solver. And then you do the actual optimization using solver.run. That's also where you provide the start parameters and any optional arguments to the criterion function. So in our case, we have a criterion function that takes a shift argument, and we'll see the motivation for that in a second. And yeah, then the optimization itself, like you get result.params as in Estimagic. To actually do vectorized optimizations, we first need to introduce the VMAP function transformation from Jax. So assume that you want to invert a matrix, but not just one matrix, but a bunch of matrices that are in a larger array. Might have 3 dimensions, 4 dimensions, whatever. Then if you try to do that just in scipy, you cannot, because it only works for for square 2D matrices. And what you would have to do is write a loop, list comprehension, or whatever, to apply the function to the subarrays. And this is, of course, very slow if you do it on large arrays. Actually, especially if you have large arrays of small matrices, it would be slow. Now, Jux has the VMap decorator for that. You take the inverse function from Jux scipy, apply the VMap decorator to it, and then apply JIT if you want, and get a compiled and vectorized version of the inverse. And now you can apply this just normally to your array of matrices, and it works. And you can also use that to do vectorized optimization. So as I said, we had the criterion function with the shift parameters, and now assume we have an array of such shift arguments and want to solve the optimization problem for each of them. In that case, we would write a simple wrapper function that does the solver.run on init params and the shift, and returns the optimal parameters. Then we vmap that solve function, can also JIT it, and get a batched solve function. And here we use the in-axis argument to vmap to specify that we actually want to vectorize only over the second argument, the first time. So the first axis 0 of the second argument. And we don't want to do anything on the first argument. And then we can do the batched optimization. And this is actually much, much faster than, let's say, using Estimagic or scipy.optimize in a loop on those arguments. Okay. You can also, as I already said, differentiate the solution. So if you want to see how the shift parameter influences the optimum, you can use, in that case of a batched version, the Jacobian from Jux on the solve function, and you say the argument you want to, with respect to which you want to differentiate, is the first one. And then you can evaluate that Jacobian at any weight or parameter vector. Yes? So the solve function is the wrapper we had written. I'm sorry for rushing this. It's the wrapper we had written about solver.run. So the thing is, you instantiate a solver. So you import a solver, you create an instance of it, and then you use the run method. This is a pure Jaxopt thing, yes. Yeah. And it's actually like, it's really useful because, I mean, Estimagic is nice, but the one thing it cannot do is have a very, very low overhead, because all this convenience functionality introduces a bit of overhead. Not very much, actually, especially if you don't use many advanced features, but a bit. And exactly in that case, it is where Jaxopt really shines. Okay. As I said, we're going to skip the last exercise sheet, but you can stick around longer, and we will also stay. Just some final remarks. So here I want to summarize the few tips that I wish I had known before I started doing my first optimization. It's, if you have a least square structure or some other special structure, try to exploit it. Whenever you run an optimization, try a few optimizers and look at a criterion and params plot. It just gives you a lot more security on whether you actually found an optimum, whether it converged, and so on. When you choose algorithms, do a first selection based on theory, but also do some experiments, either in the sense of a benchmark, if you have a good benchmark set for that is similar to your problem, or at least run a few optimizations for, let's say, 100, 200 iterations on your problem and see which one works best. Think about the scaling. So if you have a very badly scaled, or if you know that you have very different units, think about using scaling and either using the start parameters or the bounds method for scaling. If you have a very well-behaved function where local optimization is easy, use multi-start over global optimizers, because that's where multi-start really shines. And finally, if you can in any way make your problem Jux compatible, JIT it and get a closed form gradient, because it really speeds up the optimization process. I also want to show you the Estimagic team. So you already know me and Tim. Clara, Sebastian, and Tobias are all students or ex-students of the University of Bonn who have worked a lot on Estimagic. And Hans Martin is my PhD supervisor who helped get us some funding and research assistance to polish the documentation and stuff like that. Finally, if you want to contribute, and actually some of you have already said that they want to contribute, you can contribute on many different levels. So one is just make issues, provide feedback, and let us do the work. You can also improve or extend the documentation, or simply tell us what you didn't like about it. Suggest, wrap, or implement new optimizers. And also spread the word about Estimagic. Teach it to friends, colleagues, and students if you're at university. And yeah, finally, give us a star on GitHub. Makes us really happy. And yeah, I hope you will have more stars soon. Yeah, I think that's it. Thank you very much for really working on all these practice sessions until the end. We can now do a round of questions. And as we said, those of you who want to stick around a bit longer, we will also stay here. If you want to have more detailed one-on-one questions on any of the previous exercises or want to tackle the Jaxopt exercise, then you can do that.